Organic Chemistry, Chem 212, Exam 3 Material, Part 3. Alkynes, an Introduction to Organic Synthesis. Alkynes are hydrocarbons that contain one or more carbon-carbon triple bonds. Acetylene, the simplest alkyne, is produced industrial from methane and steam at high temperature. This is the industrial process, the industrial reaction. Typically, when we find really high temperatures or really high pressures, that's a very good red flag to tell us that's the industrial process, because we wouldn't want you to do this high temperature in lab to make it. Simple alkynes have the formula CnH2n minus 2. In fact, they have 2 degrees of unsaturation. Carbon-carbon triple bonds result from the sp orbital on each carbon forming a sigma bond, and unhybridized px and py orbitals forming a pi bond. The remaining sp orbitals form bonds to other atoms at 180 degrees to the carbon-carbon triple bond. The bond is shorter and stronger than single or double bonds. Breaking a pi bond in acetylene requires 318 kilojoules per mole. In ethylene, it's 268 kilojoules per mole. Naming alkynes. Alkynes are named the same way you named alkenes, except they have a YNE ending. You begin numbering at the end nearer the triple bond. On our example here, we have, coming from right to left, the triple bond starts on carbon 3. The name of this compound, 6-methyl-3-octyne. Provide names for the following compounds. Go ahead and pause the video, come back, and see how you did. All right, for the first one, ethyne is its IUPAC name. Its common name is acetylene. Your textbook really loves to use the common name acetylene, so you're going to see that a whole bunch. So you will be required to know both versions of the name. Ethyne, the IUPAC, and acetylene, the common name. On our second structure here, propyne, we have a carbon-carbon triple bond. There's no numbering system because there's no other place that could go and make a different compound, right? 3-methyl-butyne, 1, 2, 3, 4. The carbon-carbon triple bond is not numbered because, again, in this structure, just like with propyne, there's no other place it could go when you have a methyl group coming off of it. Plus, the 3-methyl gives us reference to where the triple bond was. Cyclodecyne. When they have a 10-membered ring, they like to go ahead and pucker it up like this. I also wanted to show you that if you have a triple bond on a ring, with a double bond, we put the line on the inside. With a triple bond, you put the third line on the outside. 4-methyl-2-pentyne, 1, 2, 3, 4, 5. Methyl coming off of here. In this case, we did have to reference where the triple bond is because it could have started at number 1. How'd you do? Just as we did with double bonds, you can have more than one triple bond in there. So let's take a look at these definitions. Diene, the very first one here, diene means 2 triple bonds. Ene means, ready for this, you have a double bond, ene ending, and a triple bond together. Trienes would be 3 triple bonds. A compound with 2 triple bonds is known as a diene. An ene has a double bond and a triple bond. A triene has 3 triple bonds. You number the chain that ends near the double or triple bond. Now, if there's a tie, the double bond gets the lower number if they're both present in the same relative position. But the last name is the triple bond YNE. So this is a little bit unusual. Normally, whatever gives the compound the last name gets priority and gives the compound the numbering system. This is an exception to that rule. What they decided is the double bond gets the lower number, but the last name becomes the triple bond. Let's take a look at this one here. 1-heptene 6-ine. I have, looking from left to right, I have a triple bond starting on 1, and from right to left, I have a double bond starting on 1. Whichever direction I go, they're tied. All right, if they're not tied, remember, this doesn't count, but they're tied in this case. So that means the double bond has to have the lower number, and the triple bond gets the higher number, and then you end it with YNE. 1-heptene, then you split and put a dash, 6-YNE. On this example here, my second example here, notice my triple bond starts on 1, and on this side my double bond doesn't start till 2. So this is not a situation where they're both in the same relative position. In this case, the triple bond gets to be number 1 because it's physically closer. That is not the same as the one previous. So we have number 1 here with our triple bond, 4-methyl, 7-non-in, 1-ine. Alkynes, when they're substituents, so when they don't have priority, this doesn't happen a lot, guys, but if it does happen, the ending becomes, ready for this? Alkynyl. Let's look at butynyl. I'm not even sure if I'm pronouncing that right. Butynyl. This is when it does not have priority. That means it would be on a group that has priority higher than it. Give the IUPAC name for each of the following. I tried to go ahead and add some interesting formats here, so be careful when you do these. Look for the longest continuous chain, which contains both, if it has multiple or any multiple bonds, it contains the entire multiple bond. Go ahead and pause the video, write out your answers, and come back and see how you did. Alright, this situation I have 3 CH3 groups. So I want you to go ahead, if you need to, you may not need to, I'm going to go ahead and here's my longest continuous chain, which contains the entire triple bond. The triple bond has priority 1, 2, 3, or 1, 2, 3. Oh, either direction it starts on 3, but because I have these groups coming off, this will break the tie because these now have to have the lowest numbers. The direction is in this direction. That gives me 2,2-dimethyl-3-hexane. Alright, for this one, there are no other substituents other than this longest continuous chain. I can see this starts on carbon number 2, 3, 4, and 5. 3,5-octadiene. I had 2 triple bonds. Longest continuous chain on this guy is all through here. Let's see, I have a multiple bonds starting from left to right on carbon 2. This one's definitely further away, so this would be carbon number 2. This methyl group here would be carbon number 3. I have a triple bonds on number 4. Here's 5. Ooh, and I have on carbon number 6 another methyl group, so that's on carbon number 6. 3,6-dimethyl-2-heptene, 4-ine. Let's see, I've got triple bonds coming from both ends. 1, 2. This is another carbon right here. In fact, you might want to go ahead and put a circle here reminding you there's a carbon there and there's a carbon there. Wherever you have a bend or an end, there's a carbon there, but the end of a triple bond is also a carbon. So here's carbon 1, 2, 3, and this is carbon 1, 2, 3, 4. So it's going to go in this direction. So this is carbon 1, here's carbon 2. My methyl groups, I have 2 methyl groups. Both of those are coming off of carbon number 3. Let's see if I can get my 3 in there. 4, 5. The next triple bond is starting on carbon number 5. 3,3-dimethyl-1,5-hexadiene. Alright, I have a double bond on one side, a triple on the other. Going actually from left to right would give me, let me see, 1, 2, 3, 1, 2, 3. It's tied in all directions. This is that situation where you would go ahead and give the double bond the lowest number, but you would end it in the triple bond name. So this would be carbon 1, there's carbon 2 of another double bond, starting on 3, 4, and don't forget there's a carbon here. If you want to put a circle here to remind you, there's carbon number 5 where the triple bond starts. 1,3-hexadiene, 5-ine. Okay, we have a carbon here and a carbon here, and the longest continuous chain, regardless if it bends and curves, it's going to go like that. Wow, that's pretty messed up there, pretty wiggly. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so I have octyne, and either direction my triple bond starts on carbon number 4. So these substituents that are coming off need to have the lowest number. That's a methyl group. This is an ethyl group, and this is also an ethyl group. So I can see if I take my longest chain and go this way, something's not coming off to carbon 3. This is on carbon 2. So this one wins. This one is a 2-methyl. And remember, once I choose direction, I maintain the direction. So I'm going in this direction. That's a 2-methyl. This would be a 3-ethyl. And I know it's an ethyl because I have a carbon here and a carbon here. And let's see, so that's 1, 2, 3, 4, 5, 6. This is an ethyl, 6-ethyl. And again, if you want to put little circles going, there's a carbon here and a carbon here, you can do that. On alphabetizing, the D in di does not change it. It's only the E that I'm using for alphabetizing and the M, just like we had before. 3,6-diethyl, 2-methyl, 4-octine. Preparation of alkynes, elimination reactions of dihalides. The treatment of 1,2-dihaloalkane with potassium hydroxide or sodium hydroxide produces a twofold elimination of HX. Vinyl halides yield alkynes when treated with a strong base. This reaction, if you can compare it to section 7.1, you'll be seeing a similar reaction. The difference is you're not going to have 2 moles in front of this. In this case, we have 2 moles because we're going to do basically a double elimination, a twofold elimination, forming our alkyne. It's the same set of reagents you saw to make an alkene, but because we have 2 moles, we can change our alkane to an alkyne. We can also use an alkene with HBr. This carbon right here is a vinyl carbon, so this is a vinyl halide. This can undergo the reaction to also form an alkyne. What I have at the bottom here is this product right here is a vinyl dibromide. That's how you would have gotten this in the first place. So we can see that we can go from a carbon-carbon double bond, an alkene. We can add 2 bromines across the double bond to make our 1,2-dihaloalkane, and then we can make it into a triple bond plus these other products. This is back in section 7.2. The reason why I showed you this is I wanted you to see, again, when we start doing multiple step synthesis, how we can make this, if we needed to get all the way to this. Complete the following reactions. Go ahead and pause the video, come back, and see how you did. This set of reagents, when you have a carbon-carbon double bond, has Br adding across the carbon-carbon double bond. This set of reagents is going to cause our vinyl chloride, because the chloride's on the vinyl position, to form a triple bond. Oh, looks like I'm missing a hydrogen here. Let's throw that in. Reactions of alkynes, the addition reaction of HX and X2 across the triple bond. These addition reactions of alkynes are very similar to those in alkenes. What happens is the intermediate alkene that's formed reacts further with excess reagent. And I will state if there's excess reagent so you know this reaction is happening. It is regiospecific according to Markovnikov's rule, and X in this case is either bromide or chloride. In the first reaction, the alkyne is converted to an alkene. Undergoing further reaction with excess reagent, we get our alkane, and it is going to be disubstituted. The halogens will be on the same carbon as each other. If we have X2 adding across the double bond, again, excess reagent must be shown, or we'll also mention that there's 2 moles of the halogen in there. This initial reaction gives us a trans intermediate because of the anti-addition. But when we go ahead and add the 4 halides total, because we have free rotation around a single bond, you're not going to notice that. And when we add the second halogens, they are also adding anti, so we'll see those on the opposite side. So if it's on a ring, it won't matter because you'll have 2 halogens on the top and 2 halogens on the bottom. It's the excess reagent that causes it to go from a triple bond to a double bond to a single bond. If you do not have excess reagent, you will stop at the double bond, at the alkene. The mechanism for the addition of HX to alkynes involves a vinyl carbocation. Comparing the HX to alkenes versus alkynes, the addition of HX should produce a vinyl carbocation intermediate. A secondary vinyl carbocation forms less readily than the primary. Here we have an alkene. This is the same carbocation mechanism we've seen before. The pi electrons hit this hydrogen, the pair of electrons go to the bromide. In this case, we are forming a secondary carbocation. The bromide comes in and finishes the reaction. So again, this top piece is the vinyl one, this top one is the alkene reaction that we've seen before. So the mechanism is almost identical. The pi electrons from the alkyne are going to grab this hydrogen. The pair of electrons are going to go to the bromide. A vinyl carbocation is formed. The bromide comes in and attaches to the carbocation, and now we have a vinyl bromide. Again, vinyl is the position that is on the carbon-carbon double bond. This is a vinyl position here. Complete the following reactions. Go ahead and pause the video, come back, and see how you did. For this first reaction, did you notice I put in excess? I put in 2 moles. That means we know it's going to go all the way from the triple bond to the alkane. In the second reaction, I did not put in the word excess or 2 moles, so it did stop at the carbon-carbon double bond here. This reaction, I wanted to show you on the line structure. A lot of times you'll see the zigzag triple bond where it's bent, but sometimes you won't see it bent. This is where we're saying go ahead and put a circle here and here to realize that there's carbons on each end. So the addition reaction is going to happen across the double bond, and you're going to get both E and Z products out of this. It's been a while since we talked about the E and the Z. Because this is linear, you're going to get both. Hydration of alkynes. There's 2 methods of addition of H and OH across the double bond. The first one is using a mercury 2 catalyst. It follows Markovnikov's rule and forms a ketone. If you have a terminal alkyne, you get a methyl ketone out of it. If you have an internal alkyne, you actually get a mixture of products if your R groups are not the same as each other, if it's not symmetrical. Both of these reactions involves sulfuric acid, water, and our mercury 2 sulfate. Ketones are formed in both cases, and hydrogen goes to the side with more hydrogens in the intermediate. Then the ketone is formed. This is known as a methyl ketone because we specifically have right here, we specifically have a methyl group on here. So this is another functional group you'll want to learn, methyl ketone. Keto-enol Tautomerism. Keto is talking about the ketone group, and enol is talking about a double bond with an alcohol group. This is the enol tautomer. We have our carbon-carbon double bond, and we have our OH group. That's why this is known as an enol, double bond alcohol. These rapidly interconvert where we have the hydrogen shifting. See, this hydrogen, instead of being bonded to this oxygen here, is now bonded to this carbon here, and now we have our carbonyl group. This is a ketone tautomer. This is telling us there's a rapid conversion, and because the arrow is longer in the direction forming the ketone, it's telling us that the ketone in this illustration is more favored. Isometric compounds that can rapidly interconvert by the movement of a proton are called tautomers, and the phenomenon is called tautomerism. Enols rearrange to the isometric ketone by the rapid transfer of a proton from the hydroxyl to the alkene carbon. The keto form is usually so stable compared to the enol that only the keto form can be observed. Leah for Science video, she does a very good job of explaining keto-enol tautomerism. I highly recommend you go and check out this video. Hydration of alkynes. The second method for hydration of alkynes, hydroboration oxidation, it gives the non-Markovnikov product and forms an aldehyde. Our R group, here's a carbon here, another carbon. We have the hydroboration happening and we form an aldehyde. On this side is a hydrogen we can't see. This is an aldehyde. This is a 2-step reaction. The first step is BH3. The second step, hydrogen peroxide, H2O2. On this practice, I would like you to, on the reactions, tell me what alkyne would you start off with to prepare the following. Go ahead and pause the video, come on back and check your work. This reaction caused us to form on this carbon here an aldehyde. So let's take a look at this section here. This would have been this section here. This is where our carbon triple bond would have been. It's right in through here. This set of reagents causes us to get a methyl ketone. Here's the methyl piece, there's the ketone. That means it would have been these two carbons with the carbon-carbon triple bond. This is a set of reagents where we're using mercury, and this is an internal triple bond, and the R groups are not the same as each other, so we do get a mixture of products. This right here, we're going to have the carbonyl group in one case formed here, and the second time formed on carbon number 3. So you can see I have my ketone here on carbon number 2 in this case, and I have it on carbon 3 in this case. How'd you do? Reduction of alkynes. Addition of H2 over a metal catalyst, such as palladium on carbon, converts alkynes in a complete reduction to alkanes. The addition of the first equivalent of hydrogen produces the alkene, which is much more reactive than the original alkyne, so you can't keep the alkene from reacting. You do not observe the alkene, it just goes all the way over to the alkane. The biggest difference in this reaction to the one we saw with the carbon-carbon double bond, with the triple bond, notice we have to have 2 moles of hydrogen to produce our alkane. So if you don't want your alkyne to be completely reduced to the alkane, there are some other reagents you can use. In this case, using the Lindlar catalyst allows us to stop at an alkene, but specifically a cis alkene. The addition of H2 using chemically deactivated palladium on calcium carbonate is our catalyst known as the Lindlar catalyst. The 2 hydrogens add syn from the same side of the triple bond, forming a cis alkene. And we also only have 1 mole of hydrogen because we do stop at a double bond. Now if we want to stop an alkyne from going all the way to an alkane, but we don't want the cis, we want the trans, we can use a different set of reagents. In this case, we can use anhydrous ammonium, and it's going to be very cold, minus 33 degrees. These alkali metals dissolve in liquid ammonia and function as reducing agents. This would either be lithium or sodium. And what is formed, our alkynes are now reduced to trans alkenes, with either sodium or lithium in liquid ammonia. Oxidative cleavage of alkynes. Strong oxidizing agents such as ozone, O3, or potassium permanganate, and we did see these before with our alkenes, they can cleave internal alkynes forming 2 carboxylic acids. If we have a terminal alkyne, they're oxidized to a carboxylic acid and carbon dioxide. Okay, so they added this. Neither process is useful in modern synthesis, but they will ask you these reactions on modern exams. Leah for Science video on alkyne reaction products and shortcuts. If you had a chance to look at the one for alkenes, she did the same thing with alkynes. I highly recommend you take a look at these videos on these reactions. She does a really good job of explaining these. And again, it's a summary of the alkyne reactions. She also has other videos to give you more specifics on other reactions too. So you might want to take some time to look at what she has posted for you. Alkyne acidity, the formation of acetylide anions. Terminal alkynes are weak Bronsted acids. Alkenes and alkanes are much less acidic. The reaction of a strong anhydrous bases with a terminal acetylene produces an acetylide ion. What we're going to do with this reaction is we're going to form acetylide anions, and we're going to add more carbons to carbon in some multiple step synthesis. So this is our first step. Let's take a look at what's going to happen. We're going to have this nitrogen is going to attack this hydrogen, and it's going to become ammonia, NH3. That means the sodium is going to actually hang out. That's the same sodium is going to hang out with this acetylide anion. And you want to definitely know the functional group acetylide anion. That's one that would be fair game on a test. And what's going to happen then is after this acetylide anion is formed, where it's going to undergo further reactions, because this carbon is going to want to go ahead and get rid of this negative charge and go ahead and be bonded to four things. What we do see in this acetylide anion is the sp hybridization at the carbon holds a negative charge relatively close to the positive nucleus. That's what's happening in this case. Alkylation of acetylide anions. So the anion we just made on the previous slide, we're going to add it to more carbons, and that's an alkylation reaction. Adding carbons to carbon is known as alkylation. A new alkyl group is attached. Any terminal alkyne can be converted, and this makes more carbons on carbons. This reaction has some limitations to it, so it's effective only with primary alkyl bromides or iodides. The formation of the terminal alkyne must use acetylene. So if I want to have it on the end, if I want to have my carbon from my product to be a terminal alkyne, this is the acetylide anion we had before, then I have to just start off with acetylene. Now, for formation of an internal alkyne, in this case, this again, remember this is my acetylene ion, I would actually have other R groups here, and I would be able to convert this with a terminal alkyne and form an internal alkyne. So take a look at these different R groups where they're coming and going. This first step here is forming our acetylide anion. The second step is adding whatever carbons I have here. Again, this must be a primary alkyl bromide or iodide in order for this to happen. Same thing on this reaction. You can see the same thing happening here. The biggest difference is if you want a terminal alkyne, then you're going to go ahead and use acetylene as your starting material. And in this case, we can use a terminal alkyne, and our acetylene anion will have more R groups on it than we had in the other group, and we can make an internal. And this guy here has to be primary. The mechanism, how does this work? Well, the negative charge and unshared electrons make this anion strongly nucleophilic. So my nucleophile is going to attack my electrophile, and the pair of electrons between carbon and bromine are actually going to go to this bromine. But we make this transition state. This transition state, do you notice this carbon has dotted lines to the left and dotted lines to the right? And actually this is going to be planar. These hydrogens are all planar at this point. So what's going to happen is it's not actually bonded to this carbon. I have a partial negative charge here holding on to this carbon and a partial negative charge holding on to this carbon here. So this is a transition state. And then what's going to happen is something's got to go. And in this case, we're going to see that the bromine is going to get out of there. And now my carbon is attached to the original carbon in the carbon-carbon triple bond on the end there. The reaction with a primary alkyl halide produces a hydrocarbon that contains carbons from both partners, and it is a way to make larger carbon chains. An introduction to organic synthesis. We are now going to start looking at taking these different reactions we have found and start putting them together to make multiple step synthesis. Synthesis as a tool for learning organic chemistry. A synthesis combines a series of proposed steps to go from a defined set of reactants to a specified product. In order to propose a synthesis, you must be familiar with all the reactions. You need to know what do they begin with, what do they lead to, how they're accomplished, and what their limitations are. Here's a synthesis example. We're going to prepare hexane from 1-butyne. The first step is the strategy. What are we looking at? We have 1-butyne, and I want to make hexane with it. So I went ahead and drew out the condensed structural formula of our starting material and our product. So what's the before and after picture? Well, what do you notice? What's the difference between a 1-butyne and a hexane? Well, one of the first things I notice is there's more carbons. There's 2 more carbons in there. And another thing I notice is I no longer have a triple bond. I have all single bonds. So we need to add 2 more carbons and we need to remove the triple bonds and add hydrogens. So let's take a look at the strategy here. It wouldn't make sense for us to get rid of the triple bond first, because if we got rid of the triple bond, then we would have a plain old alkane, which is very unreactive. So we really need to add our carbons first. And then after we have the carbons added, we can remove the triple bond and add hydrogens. So in our second step, we're going to go ahead and take our 1-butyne. We're going to go ahead and get rid of this hydrogen here and make it a negative charge with our sodium hanging out with it. I need 2 more carbons, so I have 2 carbons here on my primary alkyl halide, in this case alkyl bromide, and now I have an internal alkyne made, and I can get rid of that, so I rewrote this down here, by doing a hydrogenation reaction with 2 moles of hydrogen with platinum, and I can convert that to my alkane. So this reaction, I kind of dragged it out into 2 different steps like this, but let me show you a common way that this question can be asked. In this slide, I have a common format for synthesis. You're going to prepare pentane from 1-butyne. So the before and after picture, let's go ahead and put in our reactant in the first box. This is 1-butyne, and we're going to prepare pentane. I put it in red because I wanted you to see it's a different reaction than we did previously. So let's go ahead and put in our pentane. All right, what's the before and after picture? First of all, I have how many carbons in my reactant? 4, and I have 5 in my product. So I need to add 1 carbon, and then again, as we did before, I need to get rid of the multiple bond and make it an alkane. But I don't want to get rid of the multiple bond first, because if I get rid of the multiple bond, I now have a reaction. Actually, it's not even a reactant anymore. Something that's not reactive. So we've got to keep the triple bond there. What we're going to do is we're going to add our Na, NH2, and our ammonia, and we're going to form this carbanion again. That carbanion, we're going to add 1 carbon to it, so it's CH3Br. And once that happens, we have our triple bond we need to get rid of, and we will use the 2 moles of hydrogen, platinum, and now we have our pentane. So again, this is a common format for a synthesis where they'll give you different boxes and they'll ask you to put things over the arrow and that kind of thing.